of recording, which takes place during the International Geomorphology Week, one initiative which was launched by the International Association of Geomorphologists. As well as I did, maybe you heard a message before saying that this meeting is recorded. I would kindly ask you, before starting and entering into some details or making the short introductory speech, if you all agree with the recording of the meeting. If there is someone who disagrees with us recording the meeting, please let us know. Like in the previous, or like during the previous editions of our webinars, these videos were posted, were shown, were shared among our larger and larger geomorphological community, so people could enjoy the talks. They really did enjoy the last talks, and I'm very sure that they will enjoy the incoming talks of today as well. So please, if there is someone who is against recording this webinar, please let us know. Use the chat box and give us a message that you disagree with the recording of the webinar. Meanwhile, again, on behalf of my colleague Anita, that you all see here and you have all been in contact with, which was very kind in organizing all the logistics of this this webinar, and together with my colleague and good friend here, Takashi Oguchi, which traveled all the way from Japan to join us for this webinar here from the research station of the Institute of Geography in the Carvaceur Carpathians of Romania in Vrancea seismic region. And from Poland, we are welcoming you all to our webinar. Now, just some information before starting the lectures. We have some minutes available for some introductory speeches or discussions. First, some logistic aspects. Well, you all know, you have seen that you have 20 minutes. The presenters have 20 minutes to give to defend their lectures, let's say, their presentation, out of which 15 will be devoted to the presentation itself, and we are considering some 5 minutes for questions and answers, also for comments, for open discussions. We do believe that it is very important to have this feedback from the audience in order to improve our further work and to eventually publish something of a very high quality. So we really welcome, encourage all colleagues to give questions, to give comments, to suggest way in which the presentations and the results may be improved. So we'll have 15 plus 5 minutes. You will receive a notification, let's say, maybe with some 2 minutes in advance. So maybe at around 13 minutes, the presenter will receive a notification in case he or she are not looking at the time, a notification saying that they have still 2 more minutes to go. So it would be better if they go to the conclusion, if they switch to the conclusions. Meanwhile, all those which have questions or comments are encouraged to use the chat box. The chat box, put your questions, comments. Meanwhile, if you would like to address one question personally, it might be easier. Please raise your hands, and we will give floor to those which have raised their hands to make this these interventions. So use the chat, also raise your hands. Meanwhile, I think that we are all present here. We have carefully checked, Anita carefully checked the presence of our lecturers, so they are all here. We will enjoy 11 presentations out of a wide variety of topics, slope processes, mass movements, periglacial issues, fluvial geomorphology even. We have colleagues joining us from 7 countries in Eastern Europe. And again, we are very happy to have you all here with us. Anita, if there would be something that you might want to add to the presentation, we still have a couple of minutes.
I think that technically we are prepared, and I'm very happy to have you today and that we can listen and meet not only from Eastern Europe, because I see that we have also participants from other parts of the world. So it's great to share our experience and knowledge on different parts of the world, because the presentations will be not only about Eastern Europe, but also on polar regions. So I hope that it will be interesting for everyone.
True, true. Thank you very much. I see a lot of colleagues, good friends. There is Mauro Soldati, which is present. There is Achim, which is, hello, Mauro. Nice to see you in Modena. It's Achim, which I saw, it is present as well. Greetings. There is Timios, a lot of good friends and colleagues. For maybe a couple of minutes, I would like to invite Takashi to give us some feedback regarding the Asia webinar, which just ended. It was a webinar on East Asia, which was led from Romania. So speaking about International Association of Geomorphologists. Everything went well, Takashi, during the webinar?
Yeah. We had only 6 presentations, but we had a lot of discussion, and that's wonderful. Yeah, even East and Southeast Asia, we had a great diversity of geomorphological issues. So yeah, we really enjoyed them. So yeah, now time for Eastern Europe.
Yes, from Eastern Europe. So without further ado, because I see that we are just in time, then it would be nice to welcome our first presentation, our colleague from Ukraine, Anzhelika Drozdova, which will tell us about the impacts of marls fracturing on the landslide processes in the Middle Dnieper River, Ukraine. Anzhelika, the floor is yours. Good luck with the presentation. You will be the icebreaker of this webinar. Thank you very much for this.
Thank you for your introduction. Hello, everyone. Once again, I'm Anzhelika Drozdova. I'm a PhD student at Taras Shevchenko National University of Kyiv, and today I want to give you a presentation with the title Impact of Marls Fracturing on Landslide Processes in the Middle Dnieper area of Ukraine. So, landslides are mass movements consisting of different materials and extremely challenging to predict the formation, dynamic, and impact on infrastructure, which will facilitate mitigation as well as evaluation of risks. Landslides are some of the main geological hazards in the Middle Dnieper area of Ukraine. Field and analytic research proved that the landslides occur very often and their activity has increased. In recent years, the economic losses from landslides have exceeded dozens of millions of hryvnias. Many facilities periodically damaged by landslides. Prediction of future landslide hazards at the local level requires an analysis of conditions and processes controlling landslides in the Middle Dnieper area. These conditions are mainly a hydrogeological regime of the underground waters, precipitation, slope steepness, lithology of the deposits, and of course tectonic movements. Specific combinations of these factors are associated with different degrees of landslide hazards. One of the most important factors is the presence of the weak zones, joints, fracturing, etc. An indication of this factor is usually obtained by real field observation and remote sensing data. To determine the impact of fracturing on the landslides in the marls of the Kiev suit, the landslide-prone area located about 2.5 kilometers from Rzeszów to the east of the geriatric boarding center was studied. In the stratigraphy, there are deposits of the Paleogene, Neogene, and Quaternary systems. The Quaternary system in the study area is represented by modern alluvial, biogenic, lachrystine, and technogenic formations. Also common are alluvial deposits of overflow terraces, moraine formations of glaciers, etc. The Neogene system is represented by strata of red-brown and variegated clays, as well as sandstones of the Novopetrivska suit. The Paleogene system is based on a quartz-glauconite sands of the Buchatska series and the Kanev suit, marls and the sands of the Kiev suit, which are overlain by the sands of the Abuchiv, Mezhigirska, and Berekska formations. Kiev suit is a local stratigraphic unit which is lithologically consists of greenish-gray sands, glauconite quartz, light greenish-gray marls, dense with layers of dark green siltstones. The thickness of the sands is up to 10 meters and the thickness of the marls is up to 38 meters. The observation site is nearly 25 meters in height and 60 meters in width. It is located directly within the coastal zone of Kanev Reserve, where large landslides occurred. The coastal part is composed only of marls of the Kiev suit with a thickness up to 12 meters, which are covered by soil vegetation layer. The study of indicators, geogenetic and tectonic joints in the mouth of the Kiev suit is a difficult task because, as a rule, the top and the bottom of this layer could not be observed. The top could be destroyed by erosion and the bottom is not uncovered. The indication is also complicated due to the superimposed intense fracturing, the formation of which can be genetically related both to fault zones and to the brittle destruction of the stratum due to the slow subsidence of marls in the coastal part. Another difficulty is the absence of any tectonoglyphs on the fracture surfaces, which makes it extremely difficult to establish conjugate cleavage systems. Besides, the shell-shaped fracture characteristics of marls are problematic for the identification of detachment cracks. After a detailed study of the outcrop, it was concluded that tectonic secondary fractures are represented by two types: suborthogonal, which is created by two main systems of subvertical and two systems of subhorizontal fractures, and lenticular, where blocks have form of hysteresis loops. The methods of field structure and tectonic studies of fracturing, processing, and systematization of measurements, interpretation of the results are based on the standard approach to the study of tectonic fracturing described by Gzowski, Gintov, Shevchuk, Ramsey, and others. To study the suborthogonal system of fracturing, 290 measurements were made and PS diagram was constructed. PS diagram shows only two maximums of the concentration of poles, which we previously attributed to hypothetically coupled chipping fractures. Based on this assumption, the average fracturing planes are planes A and B. The sigma-1 axis was defined as the bisector of the acute angle between the planes, and the sigma-3 as the obtuse angle. So the next. Horizontal projections of the main normal stresses were plotted on a photoplan of the study area, on which two ravines were also identified. One of them is parallel to the coast. According to all indications, this ravine has developed along the surface of the plane of detachment of the shear body. The other one is orientated at the angle of 60 degrees to the coast. The erosive landforms form an almost triangle in a plan. It was undercutting on three sides by erosional forms that determine that increased landslide hazards of research area. The projected horizontal projections of the main normal stresses, which were obtained after processing of results of measurements of orthogonal fracturing, cannot be related to the subsidence process in terms of the directions, since sigma 1 is oriented almost parallel to the coast. A similar orientation of the main normal stresses is possible if a sublatitude ravine develops over a fault zone with a right shear component, the southern block of which is rising. Lenticular fracturing is widespread only in some places of the southern wall of the landslide. It has asymmetric lenses formed under condition of slow subsidence of marls, almost perpendicular to the coast, which is fixed by the destructive zones between the lenses. Destroyed products reflect the partial brittle plastic deformation of marl layer. The principal location of the hypothetical direction of main normal stresses sigma 1 and sigma 3 is shown in the figure 7. The formation of lenticular fracturing is maybe associated with the process of slow subsidence of marl body. The subvertical of or steeply deepening position sigma 1 fixes the main slip vector of the marls, and the orientation sigma 3 is the direction of dilatational expectation along the body of the landslide. So, but peculiarities of the geological structure of the landslide-prone area, its geomorphological characteristics, as well as neotectonic and hydrogeological regimes, dictate the need to develop approaches to the landslide hazards prediction and determine the parameters of landslides that are specific to a certain region. The factors of formation of landslide processes within the Middle Dnieper area have been identified based on in-depth geological analysis, field measurements, and satellite images. The role of the structural factors in the formation of landslide processes have been studied. The increased landslide activity near the geriatric center in Loche is controlled by structural causes, fracturing, lithology, slope steepness, and localization among three erosive landforms. The formation of suborthogonal fractures is associated with possible movements along the fault, and the formation of lenticular fracturing is associated with the slow subsidence of the marl body. So, thank you for your attention. Sorry, I'm some faster, but thank you.
Okay, thanks for your introduction. As you mentioned, I'm going to talk about thermo-hydro-mechanical coupling and slope stability. And I will start speaking about the laboratory experiments, and I will move then to different scales. So first of all, I want to introduce a little bit the topic, and I want to start asking why we should study temperature effects on slope stability. And the first consideration is general. because we are experiencing a global warming, and our planet is catching these effects, also a human scale, and simple equilibrium in the landscape are changing. Another point is that geohazards are changing based on the climate change, and we experience changing in magnitude, changing in patterns, and in particular in landslides, for example. And to predict these changes, we have to study carefully the climate change. And from a general point of view, the most studied effects are given by the precipitation pattern, and not from the increase of temperature, unless we are dealing with freezing and thawing. So we can say that it's quite weird that temperature is not studied in slope stability, because many how can I say, many parameters like soil strength, compressibility, viscosity that are inside the slope stability analysis are changing with temperature. So from this point of view, we can think to evaluate the change in future landslide susceptibility, accounting for the effect of temperature. So now we are going to explore a couple of material methods that I studied during this experience. And to understand the potential of temperature, I decided to study laboratory scale thanks to ring shear apparatus. And I studied also using infrared thermography analysis. Then I moved to a larger scale. As slope scale, I use some slope scale environmental GeoStudio that is able to create a subsequential coupling between temperature and hydromechanical processes. And then finally, I move a larger scale, a regional scale, using some statistical methods. So in detail, a laboratory scale, I investigated the effect of temperature in two materials, two clays. One is bentonite, one is kaolin. And I perform an increase of temperature, just increasing the water inside the water bath in my ring shear. From the point of view of the infrared thermography, I studied the behavior in the cooling phase of these two materials, always kaolin and bentonite. And their cooling phase was worth to investigate to understand how these materials are losing the heat. This is important because creating these sort of samples, I was able to understand that different materials are losing the heat in a different way. And this information can be correlated with inner material parameters that we are going to see in the second part. Now, from the point of view of the results, we are going to investigate what the laboratory scale pointed out. I investigated the effect of temperature on bentonite and kaolinite at different shear rates and different normal stresses. I was able to observe changing in the shear strength. That is one of the most important parameters in slope stability. In detail, we can observe how the bentonite is changing the shear strength thanks to the increase of temperature. I investigate a normal temperature of 20 degrees, and then I progressively increase, reaching a temperature of 50 degrees. We can also observe how the kaolin is performing in positive way. similar to bentonite, but a different shear rate. And we can also, in this detail of the imaging, see how the increase of shear strength was observed instantly. Moving to other different shear rate, we can observe how it's possible to decrease the shear strength, increasing the temperature. This is important because it means that an increase of temperature can cause a decreasing of the stability of slopes in clay materials. And in this summary, we can see how, in general, we have different behaviors based on the material. That's why we push in the direction to study different materials. Moving in the infrared thermography, we investigated, as I mentioned, the cooling phase of these two materials, and as is possible to see in the figure B, the two materials with different porosities are losing the temperature in different way through the time. These are two images of infrared, so they are thermograms to understand how it looks. And these information were used to catch the temperature at each stage of my test. As I mentioned, this is important because the way the samples are able to lose the heat is used to create an index that is called cooling rate index. And this one is used to correlate with material properties as porosity, for example. And we are able to see that there are very good correlation. And this is given by basically the possibility to catch the internal structure thanks to the releasing of the heat that is clearly connected with the porosity of the material, for example. I did the same also with the friction angle, and some interesting correlation are also visible. And after this laboratory scale, I moved to more interesting slope scale, where I perform basically 3 models. The first model didn't account the effect of temperature so it's a classical slide method from slope stability, and we observe that the factor of safety of this artificial slope in clay material is 1.05, so it's very close to the instability. Then, to evaluate the effect of temperature, I create 4 models where I accounted a general sinusoidal thermal signal, and it's possible to see that in the different seasons the factor of safety is changing based on the laboratory experiments. But I didn't stop in this analysis. I also tried to perform the change of slope stability based on global warming scenario, and we can observe that different factor of safety is possible to observe in a magnitude of 0.08. So I want to remember that in the first attempt, where the temperature was not accounted, the stability was around 1.1. And instead, when we account for the temperature, the stability is close to 1. So basically, these slopes are stable. This is very interesting, and we can see in this slide a recap. The first model was performed without accounting of temperature, the second one with a normal sinusoidal signal, and the last models with the increase of temperature of 5 degrees, according to some global warming scenario. Another imagine that is making clear what this test is saying to us is that the slip surfaces are decreasing their own stability, increasing the temperature. And we can observe that the black curve is the model that is not accounting for the effect of temperature. So we can observe that the summer model before and after the global warming are clearly unstable in many of the slip surfaces. Now, at this point, after this investigation, I decided to move a regional scale where I decided to investigate the effect of land surface temperature on a multi-temporal inventory. And the land surface temperature basically is giving us the information of the superficial temperature in average in our slope units. The inventory that I mentioned is coming from China, where a multi-temporal inventory was created after the 2008 earthquake in Wenchuan. This is very important because I use this information to understand over the time the effect of the land surface temperature. It is interesting to see that in 2008, the peak of acceleration was normally the most important factor in my model, and the temperature was not. But through the time, the effect of land surface temperature is becoming linear and quite important for my model, more than the big ground acceleration. I also performed some susceptibility analysis and some performances that were quite good for this simple model. And I performed the susceptibility maps to understand how the susceptibility was changing through the time. After this test, in conclusion, I can say that it was very important to study this topic because there was and is still very huge the gap in knowledge about landslide and temperature and thermal effects. From the experimental point of view, we started to create an experimental database on pure clays with changing of temperature. From infrared thermography, we started to use this technique to investigate the properties of the material. And slope scale, we understood that it's very important to accounting for the effect of temperature. At regional scale, we saw that some effect of temperature can be important to improve our susceptibility models. So the last slide, just to say that some outlooks are coming from this test, and the experimental evidence and the shear tests are very interesting. They should be improved with different materials. And in my opinion, this research should be studied more, and we need to more advanced modeling to include the effect of temperature. So after that, these are some references about my work, and I thank you for your attention.
So my name is Mirela Vasile. I am a researcher at the University of Bucharest. My main research interests are periglacial geomorphology, frost weathering, and more recently I am involved in an international project which also has in view geochronology of glacial and periglacial landforms in the Southern Carpathians. Moving on. So similar to perhaps Tatra and Trila mountains, the Southern Carpathians are also extensively covered with relict and inactive periglacial landforms, such as rock glaciers, which are basically debris accumulations that preserve frozen materials, frozen deposits, and which impose creep movement. In the Southern Carpathians, there are somewhat 300 inventoried rock glaciers, from which only about 40 are still inactive, which means they are still preserving ice, so in small patches, compared to the rest of them, which are considered relict. Compared to the periglacial environment, which has basically which until now had no geochronological information about. The deglaciation history is very well documented in the Southern Carpathians by surface exposure ages, which indicate most probable time of high magnitude debris productions, and nevertheless fail to, as I said before, to return a comprehensive perspective on periglacial landscapes. There were the last glacial maximum in the Southern Carpathians was set at about 20 kiloyears, which means 20,000 years ago, followed by approximately 5 deglaciation phases from 18.4 kiloyears to 16.9 kiloyears, 15.8, and the last one at 14.4 kiloyears. Among these time intervals, our questions are: where do rock glaciers stand? When they interfere in the landscape in these intervals? So therefore, our objectives were to obtain an accurate first chronology of rock glaciers formation and some information on their evolution over the Holocene, which means when debris accumulated, when did the rock glaciers had their maximum dynamics, and how come permafrost decay and their inactivation occurred. Therefore, we also try to assess the importance or the role of lithology and topography in distribution of the rock glaciers. And as a methodological objective is to test relative dating complementary to absolute dating in periglacial landforms geochronology, which we most frequently applied on complex rock glaciers. Our next slide. Our study sites were Retezat and Vagarash mountains, the central areas of these two massifs. Retezat mountains are built on granites and granodiorites, and here we had in view like 8 rock glaciers, where we mainly performed relative dating, and absolute ages are still pending on most of the rock glaciers that we investigated here. And in the central area of Vagarash, which are built on metamorphic schists, so we also applied both methods on 4 to 5 rock glaciers. In both areas, the attitudinal range of the investigated rock glaciers was between somehow 1,800 meters to 2,000 to 250 meters altitude. More precisely, relative dating, which we intended to use, we used, implies the use of a Schmidt hammer, which is a mechanical device that basically returns the rock surface rebound values as an indirect expression of rock strength, which is also used in rock weathering evaluation, and an indirect, also an indirect expression of the age of a rock surface. This means that as low is the value, as old is the rock surface, as the lowest is the value, is the lowest will be the age of the rock surface. Therefore, newly exposed rock surfaces will present high rebound values. So as a methodology for this part, we applied like 5 hits per boulder when we selected boulders from the front areas of the rock glaciers, and in the case of complex rock glaciers, from the inner ridges as well. summing up at about 50 boulders per site. The absolute dating implied terrestrial cosmogenic nuclides exposure dating using beryllium measurements. This part was performed by our friends from the Nuclear Physics Institutes in Bucharest, and they performed the physical and chemical processes of samples, processing of samples, followed by the final measurements of beryllium isotopes in Aix-en-Provence in France. Okay, moving on. This is the distribution of the rock glaciers that we had in view in the central part of Retezat Mountains, where you can see the differences between the complex rock glaciers, which are more extended, and the locations where we sampled for relative and absolute dating. Okay. Here is the distribution of the results of rebound values obtained by Schmidt-Hammer sampling. As you can see, in most of the sites, the distribution is centered around the mean value without large many outliers, but there are also some cases that the distribution is somehow not reliable, which means that we don't trust very much sampling sites such as Galescu 4 and Galescu 5. Here in the you also have the altitudinal distribution of mean values obtained by Schmidt-Hammer. We have two rock glaciers that were investigated more in detail, the Valera and Galescu rock glaciers. And as you can see, the values tend to be higher, upper in altitude, which means these rock surfaces were exposed more recently. Moving on to see the distribution, the spatial distribution of these values, as well as the values of absolute dating that we have in this area. As you can see, the upper sides of the rock glaciers have mean values of 48 to 47, while the lower sectors go to 44 and 42, which gives us a good hint that these sectors kind of evolved in the same time. As for the absolute, thank you, absolute age values, we have here an insight on Galescu rock glacier, where we can see that the frontal parts are dated at about 14 kiloyears, while the upper parts go to 12 kiloyears. This means that basically most part of these rock glaciers kind of accumulated the debris material within a time span of like two kiloyears. So we'll go back to this discussion later. This was the northern part of on the northern part of the Retezat Mountains. Now you will see in the next slide some results of relative dating from the southern side, which are quite similar. Nevertheless, here the rebound values do not differ that much due to similar altitudes and due to the fact that we don't have so many rock glaciers to compare. Okay, thank you. Next. Yeah, here is also the spatial distribution of the rock glaciers on the southern side. In Fogarach Mountains, here we on most of the rock glaciers that we investigated, we applied both methods. Next. And you can see here we have a much better view of for example, in Domnei rock glaciers, of the evolution through over the Holocene of this rock glacial body. Much younger ages, and we can see here that Schmidt-Hammer relative dating is more useful when comparing different rock glaciers rather than comparing sectors within the same rock glacier, in this case, which is Doamnei rock glacier. Okay, thank you. Next. So, as I said, much younger landforms than in Retezat, much younger, like several thousand years younger. In Doamnei rock glacier, this we have also a rock wall value of absolute ages, of absolute age. And you also can see the similar way of development as in Glacial rock glacier, where most part of the rock glacial body accumulated debris within the time span of 1 to 2 kilo years. Okay, next. So go back a bit. Do I still have time?
Yes,
Some
3 minutes left.
Findings, yeah. As we could see, most of the rock glaciers that we investigated were basically formed or initiated during the Younger Dryas, and subsequently fed up by intense rock failure activity, which we also documented from other sources, like peak activity between 9 to 11 kilo years. The largest rock glaciers from Retezat follow a different pattern, like they rather initiate in Younger Dryas or even before, being fed up in the upper parts during early Holocene, while highest rock glaciers that we investigated only started formation during early Holocene. Next. So what you here have also the comparison between the two sides, the barrier images and the rebound values. What we infer is that during Younger Dryas in Făgăraș Mountains, the pattern was rather to develop small glaciers and with well-defined moraines compared to Retezat Mountains, where rather rock glacier formation was enhanced during this period. And we consider this to be somehow also a consequence of lithology. Yeah. So consequently, we consider that rock glaciers usually derive from Younger Dryas small glaciers that formed in cirques with very high debris productions, both during Younger Dryas and Pre-Boreal. Okay, some perspectives on our work. The next is to extend the database of surface exposure ages and to couple geochronology data with paleoenvironmental data from glacial lakes in order to estimate better the permafrost distribution limit in the Southern Carpathians. Okay, thanks.
Okay, thank you very much. Thank you very much.
Okay, now I confirm that we also hear you. Thank you very much. The floor is yours.
Okay. Good afternoon, dear colleagues. My name is Alexey Novik. I'm assistant professor at the Belarusian State University, Faculty of Geography and Geoinformatics. The topic of my report is devoted to correlation of lake sediments of the southern periphery of the last glaciation in the late glacial and Holocene. Paleoclimatic studies of lakes and bog sedimentary deposits using paleogeographic methods often show multidirectional changes in temperature and humidification regime that in the same time invertal of the postglacial time in different part of the East European plain. Therefore, then reconstructing changes in the natural environmental, it is important to use a unified methodological approach and stratigraphical scales of sediments division in the comprehensive studies of accumulation by various methods. The meridional transect passing through the Belarus, Latvia, and Estonia has a pronounced gradient of the degree of continentality of the modern climate. This was also reflected in the changes in the natural conditions of the Late Glacial and Holocene, which can be traced by the example of sedimentary cores. Is in this connection using the example of the study of Belarusian, Latvian, Estonian correlation based on a multi-methodical approach. An attempt was made to trace and explain the asynchrony of changes in the lake's levels as an indicator of the climate change, vegetation, landscape, and of the largest regions of Europe, the Baltic Lake District. Cross-border correlation priority for the number of international funds and represent an important steps towards global correlation of paleogeographical events in the history of the Earth. It should be noted that in order to reduce the influence of local factors affecting the nature of sedimentation and as a consequence of changes in the course of levels, it is necessary to compare lake systems in similar landscape geomorphological conditions. Trend in changes in lakes levels were made according to the general accepted methodology of comparative analysis. The Usa lakes within the Otepää uplands in southern Estonia, the Kuja lakes within the Vidzem upland in central Latvia, and the Daugaja lakes within the Tsintianske upland in northern Belarus were selected as reference objects of the studies. The choice of these objects is due to single glacial genesis and similar features of the location of lakes with the various marginal stage of regression of the Würm glacier. It also due to the study of the history of development by various paleogeographical methods, not only of lakes, but also of their catchments. This allows you to track the possible amplitude of the changes levels. It is important to note that the catchments of the studied lakes are composite mainly of water-resistant moraine loams, which are the least sensitive to the weakening on infiltration processes. This factor, along their position in the depth-cut glacial depression on elevated catchments, created the regime of filtration of levels sensitive to climatic change, which was reflected the change in the nature of lake sedimentation. When studying the exposed sediments and the clarifying in the age of lithological horizons, a complex set of methods was used: lithological facies, spore and pollen, radiocarbon, geochemical, and isotopic. The European continental stratigraphic scheme of the Late Glacial and Holocene was used in the stratification of sediments. Information on the distribution of the main sedimentary rocks, as well as orogenic matter, micro, and macro elements, was used as indicator of phases of the development of lakes. The informative value of geochemical indicators depend on the nature of sedimentary complex of the catchment area, its genesis of lake depression, and the location is well. The depression of Lake Usa and the wetland depression of the catchment separated by hills have glacial genesis. Within the lake depression in Korea, Usa 1 was used to analyze the dynamics of the lake's levels. On the southern western side, the ledge blocks follow adjoins the lake depression, within which Korea Usa 2 and Korea Usa 3 were analyzed. Analyzed and comparison of isotope oxygen and palynological and chronostratigraphic, excuse me, and chronostratigraphic data indicated that the beginning of the lake sedimentation in young areas in the lake's catchment area. It was associated with the activation of glacial karst processes. The catchment area Lake Usa characterized a pronounced, strongly deserted highly moraine relief. Korea Closure 1 was made in the central part of the glacial karst lake depression. The Closure 2 core is described in the geological outcrop of the northern shore of the lakes. Analyze and comprehensive of palynological and chronostratigraphic data showed that lake sedimentation in the catchment area of Lake Closure began in early period as a result of activation of glacial karst processes. The Lake Doge occupies the centralmost subdepth section of the vast macrohollow. Core Doge 1 is made in southern part of the depression, the Lake Doge. Core Doge 2 was made in the northern part of the Doge hollow within the peat bog massif. According to the pollen and radiocarbon data, the formation of the basal peat horizons in the catchment depression of the Lake Doge occurred at the beginning of the late glacial period, during and older years. The Aleriot and Dries, in younger years, there is a tendency to decrease in levels, which increase in intensity of carbonate accumulation. Based on the analysis of the conducted paleogeographical studies and reconstruction of the change in the levels of lakes in Belarus, Latvia, and Estonia in the Late Glacial and Holocene was carried out. During the reconstruction of lake layers trend, a number of general patterns can be clearly seen. First of all, it is clearly definite minimum of levels characterize the early stage of the late glacial period in Lake Doge is recorded. The low position of the levels apparently were due to the sharp cooling in this climate of this epoch and this incompleteness of the processes of the conservation of glacial karst. Slight increases of the water contents of the territory that occurred in the alluvial beginning of the younger years are observed in the Lake Closure and Doge, which is associated with the warming of the climate of this time and the activation of glacial karst processes. The deepest of lake depression of southern Estonia in this time remained preserved by ice. The increased cooling in younger years was probably accompanied by the increase in climate humidity and the rise in lake levels. At this time, the lake levels user and usually the intensification of groundwater supply caused an intake on carbonate and heterogeneous materials and the beginning of the formation of lake sediments. However, already in the first half of pre-boreal, there was a tendency to lower levels for the all studied lakes, which was associated with the decrease of climate humidity in this decrease of fluvial activity. At this time, found of lower power layers in ancient peat are recorded in the all studied lakes. The beginning of climate warming and this activation of the processes of unloading towed waters in permafrost due to increased infiltration processes facilitated the formation of peat. And since the second half of pre-boreal, region-wide dynamics of lakes levels rise has been observed in the studied lakes, whereas due to the global trend of warming and humidification of the climate is beginning of the Holocene. The mineral and organomineral deposits in the lakes in the late glacial period, which prevailed up to this time, begin to overlap beach rocks of carbonate composition due to leaching of the carbonate moraine as a result of increased fluvial activity. In this time of sedimentation of carbonate sediments of the lakes had the character of the oligotrophic mesotrophic reservoirs with a low contents of organic matter in bottom sediments. The morphological features of the lakes, depressional and lithology and catchment rocks were is great important. The processes of increasing levels continued until the middle of boreal. Another called snap that occurred at this time led a decrease in humidity and decrease in levels. At the end of boreal and beginning of Atlantic time, there are processes of stabilization of levels, which a general tendency to increase, but already about 7,000 years ago, the stage of next lowering of the levels has come, which reflects the interruption of lake sedimentation in the core in the littoral zone of Lake Dolge. This time, there is change in the nature of sedimentation in all studied lakes. The predominant carbonate components in lake sedimentation are decreased by the Middle Atlantic, or is completely replaced by organic mineral. The reasons for the change of carbonate deposits to organic ones were complex. Leaching of catchment area, which leads to reduction of the inflow of hard water, cooling at the beginning of the subboreal period, which determines the stopping or slowing down of the formation of lake carbonates, and increase the trophic status due to the development of animal and vegetable life in them. Cold and humid subboreal condition contributed to the onset on other trend in increasing levels, which is reflect an increase in mineral components in the sediments of all lakes. In addition, in former littoral parts in the Lake Dolge, the processes of lake sedimentation is resumed. In the second half of subboreal, the nature of fluctuation was often diverse, apparently due to the local factors, but by the beginning of subatlantic. The processes of warming and humidification of the climate caused another general phase of uplift in the all studied lakes of the region. Currently, the analysis of the lake sedimentation confirms the stage of regression in the dynamic of the change in the levels of the studied lakes, which began about 1,000 years ago. As can be seen from the above paleographical analysis, most recorded patterns of the lake sedimentation have common trend for the Baltic Lake district, which is associated with global paleoclimatic change in the Late Glacial and Holocene. However, in the climatic cycle,
2 minutes, sorry, 2 minutes remaining. Thank you.
Okay, thank you very much. However, in the climatic cycles associated with period of cooling and increasing humidity when moving from the northwest and southeast, a certain delay in the stage of fluctuation of lake levels, and as consequence, change in the nature of sedimentation are revealed. Conversely, for paleocycles with warming and the decreasing humidity, in reverse pattern of events is observed, which in addition to the influence of local factors in catchment areas can be explained by increase in the gradient of the degree of continentality of the climate along the meridional transect of the lakes Yuza, Kuze, and Dolge. This is also confirmed by palynological data according to which late boreal, mid-Atlantic, and early subboreal cooling is reflected is an increase in content of pollen in deposits of cold-resistant vegetation and decrease the proportion of thermophilic vegetation. Okay, thank you for your attention.
So thank you so much for the introduction, and good afternoon, everyone. And welcome to my presentation. My name is Mateusz Suwiński, and I study environmental geoinformation at NCU in Toruń, Poland. And as it was said, the subject of my presentation is quantitative reconstruction of the glacial lake outburst flood based on megadunes morphometry, Northeast Poland. So the presentation is structured as follows. Firstly, I want to bring you a little closer to the definition of lake outburst floods. Then on a few slides, I am going to show information about Suwałki mega flood in Northeast Poland. Later on, we'll get to know my study area, which is surroundings of Serwy Lakes on Augustów Plain. And in the final part, we are going to see construction of the database with morphometric parameters of megadunes and based on them, a reconstruction. What we have here is a concept of glacial outburst flood. We have, maybe I'll switch on a laser for that. We have here a glacier, a pro-glacier lake, terminal moraine, and glacial lake outburst flood because of the breakage of this moraine, of this dam. So glacial lake outburst floods are just a sudden release of water from a lake formed somewhere around the glacier. And we have this information shown here that the glacial megaflood is counted when discharge is more than 1 million cubic meters per second. But according to Carling, it is not required every time. It is not a strong factor. So here, left side, there is a global map with marked occurrences of GLOFs. So it is glacial lake outburst floods, and the special one shown with the star, Suwałki mega flood. Right side, we have two charts, and I want you to know from these that the increasing processes magnitude associated with increasing time of processes duration, and glacial floods are extraordinary processes. During short time, significantly, this is shown here, they transform proglacial area. And in Icelandic language, these are called jökulhlaup. Sorry for mispronunciation. And they are occurring around the world, so there are different names for that. There's an example of Hubbard Glacier in Alaska. And we have different factors. We have different water sources shown here, physical, geographical factors, the most important hydrological conditions, large supplies of meltwater and temporary retention possibilities, different types of dams and dam breakage mechanisms, for example, erosion, water pressure, or even earthquakes. So I want you to focus on this area, which is southern part of Scandinavian ice sheet with marked major margins retreat during the last glaciation. Our megaflood in northeastern Poland is shown right there, and it occurred during the Pomeranian phase, somewhere around 18 to 16,000 years ago. So there is the line of this phase, right? We're going through Lithuania, Poland, Germany, and to Denmark. A closer look at Polish Sandur or Outbush plains. And we have another glacial phases shown and ice marginal valleys. These are the ways of meltwaters from ice sheets, the main roadways. And as it mostly described, these meltwaters were going to the west mainly because of the elevation level characteristics. And I want you to see that there is another a little closer look at our study area. So we are here in northeastern part of Poland. And we have here different regions. We have Western Suwałki Lakeland and Eastern Suwałki Lakeland, which are places that during the Pomeranian phase there was an ice sheet. And we have an Augustów plain right there, which is a Sandur plain. So the sediments of fluvial waters are right there. And in 2019, there was published a geomorphological map for this special area, because this is the area of our glacial lake outburst flat. So there we have it. You can see main 2 or 3 parts of this map, this brown and pinky violet colors, and these yellow and greenish ones. They are parts of subglacial and proglacial landforms. Subglacial are mainly GCLs or subglacial tunnel valleys. Like we can see here, Great Sherman Lake, Hańcza Lake, which is the deepest lake in Poland. And we have this proglacial landforms part that is mainly on outwash plain, sandur plain. And we have different gates, which are the mouths of meltwaters, of these mega floodwaters. So these 2 systems are different from each other, mainly because of that the water in subglacial part, because of the ice sheet pressure, is going upstream, like we can see with this arrow right there, through tunnel valleys. And then the water goes through the gate, which is like a border of the ice sheet, and then it goes like in natural environment without pressure, it goes downstream and create another different forms on outwash plains, like we see here. So we have first order landforms like spillways, outwash plains that were shown before, these yellow colors, but we have many others, second order forms made from the meltwaters. And I want you to focus on megadunes, which in this case are huge, sandy, fluvial, regular, and asymmetrical ridges, which are the result of redeposition of the sediments transported by mega floodwaters. And I want you to have a quick look on my bachelor paper. So we have this part of the region that was shown in the geomorphological map. We have Bachanowo Gate, we have somewhere the Prudziszki Gate, and these are my studies, mainly microscopic studies on sediments. And we have here Athene, which was, and these are samples from megadunes. And as you can see, there was a usage of Kaye analysis, so degree of rounding and type of grain surface, and automated analysis made by CAM-Sizer M1 analyzer, where it uses like static pictures analysis of the grains. And I wanted to focus on sphericity, so this is another factor or parameter of roundness of the grain. So this is telling us how much close the grain is to the perfect sphere. And as you can see, the results are that the sediments of the megadunes originated from in older environment than 16 years ago, because of this high percentage of well-rounded, spherical grains. And as you can see, different layers of the megadunes have different dominance of Kaye and Krumbine groups. So these are more fresh grains, more broke, which are a more periglacial type of grain, or more Aeolian type of grain. So there's a little explanation for the for my profiles that are shown right there, because I wanted to show, I wanted to describe the slope. So we have height difference in meters divided by distance on the profile, and this is based on them 10 meters them. So we have the first profile A, the Rospuda River Valley. We have slope 0.0032, and then we have Augustów Plain, which is almost flat, and we have here second order valleys. We have another, this is actually a profile C, so right there we have just not a huge slope, as you can see, and then we have a much longer B profile with western spillway and again almost flat Augustów Plain. These again are almost flat, very close to a perfect flat areas with second order valleys. There are some lowered areas and elevated ones. And as you can see here, most of the region in G and H megadune fields are lowering to the east. And as I said before, they should mainly go to the west, like in ice marginal valleys. So the study area exact is here. It's a part of this geomorphological map. And we have here a really complex area. As you can see in this part of Poland. And there we have some megadunes crest lines shown right there. It's a pretty messy and complex area, but I tried to find a way of the water flow main in this region. So there are two main directions, as you can see, and now they are combined. So I collected relevant information from cross-sectional megadunes profile based on 1 meter dam. Then I calculated the morphometric parameters of megadunes, so heights and lengths. And then the quantitative reconstruction based on megadunes morphometry was created. As you can see with kernel density, I've shown different groups of the parameters.
2 minutes left. Mateusz, sorry, 2 minutes left.
Okay, thank you so much. Yeah, so we have here a length of stoss and lee slopes, of course reduced based on the two-dimensional area. We have heights of stoss and lee slopes and different kernel density groups. We have different histograms right there. So we have here L divided by H2 parameter, which is like a megadune elongation parameter. We have here another groups distinguished by these white lines, and another parameters. But as we can see, stoss slope is usually in megadunes is usually much larger than lee slope, and when we divide L1 and L2, we can see that some of the forms are have stoss slope much not that large length. So maybe they're primary megadunes transferred by water from various sources, or these are maybe bed forms of high energy supercritical flow, like in Brudziszki Gate right there. So the final quantitative reconstructions, we have different equations used for show the flow velocity of different groups of megadunes, based on different groups of megadunes. They differ between almost 7 to even close to 1 meter per second. Yes, we can even see that it's almost 7.5. And we have here an total average of these reconstructions, quantitative reconstructions. So what's next to be done? What's next to be done is cluster analysis.
Conclusion, please.
Yes, this is a conclusion. What has to be done is cluster analysis, so extraction of morphogenetic types of bottom forms. Fieldworks must be done to confirm genesis of the landscape, and hydrological modeling, which helps us determine the main directions of the glacial flood flow in the proglacial zone. And thank you so much.
So, hello everyone. My name is Zofia Owczarek, and I'm a PhD student at Alfred Jan Cold Regions Research Center at the University of Wrocław. And I'm going to tell you, draw your attention to the morphodynamics of Svalbard's barrier lagoon systems, and they respond to the cryosphere accelerated degradation. So my plan for this talk is as follows. First, I would like to say a few words about the development of research about Svalbard's coasts over the past 20 years. Then focus on lagoon barrier coasts, which are my point of interest. And after this introduction, I will present the observed changes on Svalbard lagoons and also show some paraglacial lagoons, which seems to be a particularly interesting type of lagoon. Moving on to the end, I will show you how glove events can affect the coastal zone. And the goal of my presentation is to present the state of Svalbard's lagoon barrier systems since the end of the Little Ice Age. So starting with the development of research on Svalbard coast, we can say that the last 20 years of research has been a significant progress made. This is important from because for many years, Svalbard and other high Arctic archipelagos were somehow neglected in research initiatives, focusing on coastal zones and change research. As you can see on the map, between 2005 and present days, number of studies focus on coastal change, with a particularly interest in the relationship between retreating glaciers and development of deltas and barrier fed by sediments from glacial rivers. And researchers from Wrocław carried out research on rocky coast and state of Svalbard on coastal permafrost. And finally, in the last few years, a lot of research effort concentrate on coasts exposed to the retreating glaciers. And here you can see the Brepolen Bay on the left side of the slide. And all of that studies provide that Svalbard coast were very sensitive to landscape transformation from glacier-dominated into paraglacial-dominated one. And however, still this research concentrate on response of barrier lagoon systems, which are one of the most sensitive coastal environments of climatic changes and sea level changes in other morphoclimatic zones. And during my literature review, I have found only few cases on development or erosion of Svalbard. For instance, Professor Ziaja and his team describe how erosion lead to disappearance of Davis Laguna, and this is on the right slide, on the right side of the slide. Also, last year, remote sensing analysis allowed Professor Urbański to automatically classify Svalbard high Arctic lakes with subdivisions of coastal lagoon, but only larger than half a hectare and without Nordaustlandet. The Norwegian Polar Institute published a report on ecology of Svalbard lagoons, but larger than 5 hectares. So it's really big, with this only big ones. In my research, I tried to check what happened to Svalbard lagoons since the termination of the Little Ice Age, and how sensitive they are to changes in glacier sediments transport, sea ice, and storminess. And now you can see that the State of Environment Science in Svalbard Report 2020 shows that lagoon barrier coasts, and maybe I will have this laser, like here. Barrier coast or low slope soft coast occupy about 29% of Svalbard's coastline. And as you can see, there are like many new lagoons appear in 2021 on the unclassified coast on the north and Nordaustlandet. And need this anymore. The increasingly long season of ice-free coasts in this island allows the formation of coastal lagoon. Like lagoon barrier coasts are particularly interesting because of their sensitivity to sediment supply and sea level changes. And so now, how does lagoon form? So Orto in Encyclopedia of Coastal Science shown that lagoon can be formed in different ways. First way is an inundation model. When sea level rise causes the flooding of coastal valley, and when lateral beach migration creates a partial barrier between the flooded valley and the coastal sea, we have like lagoon. And the second way is a speed embayment model. Lateral speed migration creates a partial barrier between the coastal sea and a recessed section of the former ocean coastline, and the barrier speeds embays the recessed coastline and the former shore face. On Svalbard, this second type of formation lagoon is more common. And now something about the data methods and troubles. So to identify the lagoon of Svalbard, I used the orthophoto map from 1936 published by Gaiman et al. In 2022, as well as satellite images of the Sentinel-2 mission from 2021. Manual identification was carried out in ArcMap software and allowed me to find smaller lagoons that have been overlooked in previous studies. So the number of lagoon in 1936 differs significantly from those in 2021, but this is mostly due to the poor condition of the orthophoto map, which made it impossible to determine the existence of lagoon, which you can see as an example in the first map. In addition, on the figure on the right, there's like a rocky basins submerged by water, and they don't developed in bicoastal sediments. They look like lagoons, but they are developed in different ways. So this is like catchy example. And here you can see some statistics about the Svalbard lagoons. Many new lagoons have been created, mainly accumulated in the north of Svalbard, which you could see some slides before. And this is mostly because of the free of sea ice coasts. What's more, I've noticed that lagoons are also concentrating in places from which glaciers retreated. There are almost 38% of lagoons which I found on Nordaustlandet, they are located there. Comparing this to the Spitsbergen, which is like twice larger in area than Nordaustlandet, makes it a really interesting case. And by no data shown in the table, I mean the inability to determine if a lagoon occurred or on this particular location of the poor quality of the orthophoto map, which you can see like example before. Now I present you some examples of paraglacial lagoons, which are formed by the retreat of the glaciers and the barrier that separates the lagoon from the open sea or ocean is usually composed from the remnants of the frontal moraine left by these retreating glaciers. So I have found like 36 examples of paraglacial lagoons on Svalbard for now. And here you can see how one of these paraglacial lagoons developed. Since this lagoon has no official name, I'm calling it Makarov Lagoon, after the glacier Makarov-Bren, which is connected with this lagoon. And by 1938 to the present, there was a retreat of Makarov-Bren by 1.5 kilometers, and sediments released from the glacier was accumulated on the remaining moraine, creating the barrier that made the Makarov Lagoon. And since the 1938, about 350 meters of new barrier have been formed, resulting in a growth of barrier growth rate of about 4 meters per year. And this in coming months, I will work on stages of such lagoon formation, particularly in those sites where glaciers are already on land. But of course, there are also cases where lagoon already existed in 1933-36 and they was destroyed by erosion. In the picture, we can see the same places in 1936 and now. As you can see, such cases happened in different environments, in fjords or in open seas in the north or south of Svalbard. And the second lagoon on the right side of the slide shows the Davis Lagoon, which is described by Jaya and others, which I mentioned before. In this case, the land moves by erosion by more than 400 meters. And final example, quite extraordinary, the examples which I show you before are standard processes on lagoon formation or degradation on Svalbard. However, during my studies, I have found one interesting case where the lagoon was destroyed by the glacial lake outburst floods. We know now what the glacial lakes outburst floods are from the previous presentation. And these are extreme events that can lead to serious changes in the environment. And the map shows a small catchment area, a small Arctic catchment in northwest Spitsbergen, with glacier connected and with glacier connected to glacial lakes and lagoon below them. This is the place that my team and I have been studying with remote sensing methods. And we were able to detect how drastically the GLOF has affected the coastal environment. So what we look at when we look at the figure, we see that on August 1st, last year, there was water in the lagoon, the first pictures on the left. However, on August 16th, the same year, there was no water. During that time, the glacial lakes above the lagoon have significantly reduced in size, and the glacial lake at Knivsegbrunn has almost completely disappeared, such as the lagoon below the lakes. And lower NDVI values were recognized in the runoff zone, suggesting that vegetation may have been destroyed by the flood wave. And our team believes that the lack of water in the lagoon is related to filling the lagoon by sediments during the GLOF events, making it difficult for water from the ocean to enter again. We can see in the photo 10 days later, maybe I will use the laser to show this. I don't see this in here.
Meanwhile, sorry, 2 more
Yes.
minutes.
Okay, thank you. So we could see that place. So 10 days later, after the event, water appears in the lagoon, but only near the inlet where the entrance is the easiest. However, to confirm our observation about the lack of water in the lagoon by filling the bottom with sediments, we would have to visit the area of Rekvet Bukta. Who knows, maybe in the near future we will, I hope so. And summarize my presentation. Since the termination of Little Ice Age, 114 lagoons have been formed in Svalbard. 9 lagoons have been eroded or become coastal lakes. Most of the new lagoons were formed in the northwest, in the northern part of Svalbard, and a new type of lagoon, paraglacial lagoons forming in front of retreating glaciers has been detected. There are like 36 systems like that currently developing on Svalbard. And Gulf events have the potential not only to transform glacier forelands and valleys, but also may modify coastal landscape and landforms. So my future research, I would like to focus on finding the answers. What is the main reason for changing in lagoons? Is the opening and closing of lagoon related to constants and long-lasting wave actions, or maybe it's more influenced by extreme processes such as storms or gulfs? And now I would like to acknowledge my research mentors and partners, Professor Mateusz Suwiński, PhD Marek Kasprzak, PhD Jan Kawan, and my closest colleagues, Aleksandra Wosz and Iwo Wieczorek. Thank you for helping. And this is a contribution to Aspire project funded by the National Science Center in Poland. And thank you for your attention. I leave my email for contact. And if you have any questions, I will be happy to answer. I hope I was in time.
Thank you, everyone, and hello again. Good afternoon. My PhD title is Use of Aerial and Satellite Images for Dynamic Analysis of Vegetation in River Landscape. And my advisor is Dr. László Bertalan from Slovak Academy of Science. So we start with some introduction. Remote sensing and reference. As you know, remote sensing is a process of detecting of physical characteristics of area by distance, usually with satellite or aircraft. And when it's come to riparian zone, despite the relatively small coverage along the river system, riparian vegetation plays a crucial component in river system, and it also have a reciprocal interaction between water flow and morphology and also the vegetation. Vegetation dynamics also have a mutual interaction between biodiversity, soil conservation, sedimentary process, and also aquatic ecosystem and water quality. As you can see on the screen, river flow always is in a contact between bank stability, filtering, shading, and so on. And it means river flow is as a in fact, to the vegetation and also the quality and the health vegetation based on the river flow. Our main aim for this study is the classification of vegetation by combining aerial, satellite, and LiDAR data in order to identify vegetation response to succession and human impacts in riparian zone. There is a comprehensive literature about studying riparian vegetation. As you can see, a lot of these researchers focus on available tools and perspective for manager and effect of flood on vegetation, land cover and land use in riparian zone, and also vegetation variable from field survey and remote sensing data. And basically, this literature just was an inspire us to just do this study. Well, we have two different study area. One in the south of Slovakia, in Danube River, and relatively is a large river. And second one that is a small river in the north of Slovakia, named Bela River. Actually, this two study area is completely new for me. And I haven't studied this area, and we are going to just monitor these two rivers. Okay, let's go to the aims and hypotheses. We have two main aims for this study. The first one is using automatic classification to identify channel revitalization effect on vegetation properties using multi-temporal optical satellite images. Beside of the main aim, we have some subtasks for this study. First one is testing different classification method of basically satellite images to achieve the high accurate classification map. Second one is identify the effect of different environmental parameter and human impact on vegetation, a spectral response. And the third one is identify vegetation health before and after revitalization. Our hypothesis for the first aim is direct human impact and downside of revitalization, improve health properties that significantly respond in spectral values expressed by vegetation indices. The second one is develop methods and workflow for long-term monitoring of riparian zone by a combination of aerial images that it has high spatial and low spectral resolution and low temporal density. With satellite images that they have low spatial and basically high spectral resolution and high temporal density for vegetation dynamics and succession analysis. As our subtask for this aim, we are going to classify of aerial images to identify different type of vegetation association, improve classification of aerial images using textural properties. Third one is identify temporal vegetation dynamic for different time horizon. And the last one is explain the effect of environmental parameter on vegetation dynamics. Beside of this hypothesis, that is a combination of textural and spectral properties, basically improves the vegetation classification accuracy of historical aerial images. As we have vegetation age detection and also geomorphic parameters, these two components will create a homogeneous object that will help to object can be monitored by low resolution satellite data. Basically, in this aim, we are going to extract some homogeneous object from high resolution aerial images to create the object and use it for low resolution satellite data. Basically, our methods focus on image analysis and classification techniques, change detection, temporally and spatially, and assessing morphological features in basically high resolution images, and extract information from satellite images, and also creating model for predict the future change in riparian zone. There is our workflow in flowchart for this study. As you can see on the top, we have Danube River, and we are going to use Sentinel-2 images, and also combining with LiDAR data and also ancillary data, include morphological feature, climatology, hydrology, and geology. And after, as you can see in green arrow, at first we are going to apply some pre-processing to satellite images, like atmospheric correction and geometric correction, and then extract some vegetation indices like NDVI, SR, and there is an abbreviation here in the right up corner. And also we are using primary data or ancillary data to extract environmental properties like erosion, groundwater, high above channel discharge. And after that, these component and criteria go to the 4 different machine learning algorithms, like SVM, random forest, conventional neural network, and graph neural network. And after train and test our training samples, we will apply this for classification method. And after achieving the classification map, basically we have done accuracy assessment to just make sure our classification map is very accurate. And after that, in first part, we are assessing the vegetation response before and after the revitalization. And this procedure is also for Bela River, but in Bela River, we are focusing especially on historical aerial data set. And for this procedure, we also extract some vegetation indices from satellite data to just incorporate to final classification. And also we are going to extract some textural properties from this historical aerial data set. And we are using these textural and spectral properties for this machine learning algorithm, like a support vector machine, random forest, CNN, and GNN. And we have the same procedure like Danube River, but we use different data set. And after train and test our sample data, we will achieve the classification map. And after that, we will achieve the vegetation age map and successional change. And finally, we will just extract some object from these historical images. And as a final aim, we are to evaluate vegetation monitoring and their response in second study of area. So that is the end of my presentation. Thank you so much for your attention. And at the end, I'd like to thank Dr. Miloš Rusnak as my supervisor. And I am ready to here some recommendation and answer to your question. Thank you so much.
Thank you all of us, and thank you for watching and listening. My name is László Bertalan, and I'm from Hungary, as been mentioned. And what I want to show, continuing the series of fluvial topics in this webinar today, I would like to propose novel methods that we apply for surveying hydromorphology in small rivers, which can be a different scale compared to the Danube River that we have seen in the previous presentation plans. So first of all, the problems, why we have started to work on that. In Hungary, we have the major rivers like the Danube also is flowing through Hungary, which are regulated, and the major rivers are already regulated. We don't have that much of problems within agriculture, except the drought. But in smaller rivers that I presenting to you today, the Shire River has just only minor influence, and only minor river regulation has been took place within the past decades due to financial issues. And so what we can observe within these rivers is the complete almost semi-natural state. That means that free-forming meanders can occur in several alluvial plains, because these rivers are flowing across alluvial plains in the Carpathian Basin. And since we didn't have in the half of these pathways, we don't have direct influence, then they can freely meandering. So what means it also that they can produce several bank erosion processes. So as you can see from these examples here in these first slides, almost all of them are at the edge of agricultural productions. So our first plans a few years ago was to detect those areas within these river reach, which are mainly influenced by river bank erosion and river meandering processes. And the problem is that these rivers were not that well studied, because like the traditional survey boats that are used for mapping large rivers like the Danube or the Tisza River in Hungary, they are not possible to navigate within these rivers, because just to mention these, the scales, these rivers, the mean channel width varies around 30 meters, and the mean depth can vary from 0.5 meter to 2.5 meters. So from this point of view, we needed more higher resolution imagery, higher resolution data. And the Water Management Directorate usually applies some geodetic surveys to do cross-section surveys. But for example, their frequencies, like in every few hundred meters, they can do a cross-section. So we needed more information. Of course, we applied archive imagery, and then the advancement of UAS and UAV drones brought us the possibility to monitor these bank erosion processes in high spatial and temporal scales. However, in that period, we had problems with seeing below the water. Of course, we were just doing the lateral changes. So our first step was before to reveal the spatial morphodynamics along this river, and drones became absolutely efficient in this way, because we were able to detect these morphological changes. But you can see a few examples, a few really intensively meandering river sections and bends. And for example, here, if we quantify the several time periods when we were applying drone surveys to provide orthomosaics, what we can see in this figure is within these numbered transects, you can see is the cumulative erosion that can exceed even 40 meters in 5 years. So as you can see, since this is a small river, like in a few years, it's the same amount of bank erosion and lateral movement can be identified as the mean channel width. So we needed more data, and we needed to reveal the possible drying factors, because these farmers here and also the scientific community are interested more, not just what happened and what's happening here in the recent processes by this monitoring, but they would like to see what to expect, how to forecast even these morphological changes, morphological evolution, and the possible, let's say, affected agricultural areas. So in that case, we need more details. And as I mentioned before, the traditional boats, as you can see in this example, in this section that I will also show you the details, they're quite shallow. And the labor-intensive and time-consuming traditional surveying methods can limit our goals. For example, for detailed hydrodynamic modeling and hydromorphological modeling, we need better time series of morphological change and even hydrological data. And in data-scarce environments like this, I mean, here in the closest gauging station is like more than 25 kilometers upstream. So for more reliable data, we needed new environments that can provide almost like in situ information about the flow characteristics and also the changing riverbed. So that's why we applied a joint project with several of my co-authors that I presented in the opening slide, a nice project with German colleagues when we were working on the development of tools that can be applied for these shallow and smaller rivers. And this included several things like including air, ground, and water-based surveys. And what I will talk today is more on the UAV part, like the drone-based sensors to quantify morphological characteristics. I mentioned the flow information is absolutely important to know something about the local morphodynamics. The most reliable way is to use the ADCP sensors to reveal even the depth averaged or even the surface flow velocities. But as you can see, I mean, here in this section, I plotted 4 transects that took a day to survey. So that's why we need a bit more higher resolution, even in a spatial context, to reveal this information. How is changing even the flow structure within this meander bed? And also, this is the flow part. And how about the bathymetry? Because I mentioned the traditional survey boats are not capable to navigate. Traditional UV SFM-based surface reconstruction is widely used, not just in our methods, but in many cases, it's really high resolution data can be provided from the floodplain. But there's been limitations under the water if it's not clear and there are many refractions and it's not a flat terrain. So our purpose was within this project to develop methods that can somehow reconstruct the bathymetry and do some correction within the refraction. So what I will also propose a few examples from other rivers from Germany, Freiberger Mulde, and also the Pullmonkey River in Finland, when we tested this methodology to somehow provide better results. If you're interested, you can read the paper below, but briefly what I would like to summarize is the method developed by Annette Eltner, my colleague, is using drone-based footages and also the SFM mapping imagery to at least to reconstruct the surface of the floodplain, and also to apply the SFM photogrammetry and the so-called refraction correction to reconstruct points, 3D points of the channel bed. Of course, you will see there are some limitations also, but it's a tool that can have continuous data on the flow velocities and the bathymetry as well. And in the meantime, yeah, the 2 main outputs is the bathymetric 3D point cloud and the flow velocity tracks. If you're interested, of course, the details, I'm not showing every details here. You can read the paper. These are some preliminary results on these above mentioned 3 river sections in 3 countries. But in this topic that I mentioned today is the Shire River. As you can see, it's really detailed, high resolution point cloud on the bathymetric reconstruction. However, what you can see is the dark spots are blank areas because these methods, and since this is RGB based survey, if it's too dark, if we cannot see the riverbed or there's too much turbulence and turbidity, it can of course limit the application. But that's what we are testing, what type of conditions can provide the best results. And in the meantime, we also can visualize the surface flow velocity magnitudes. Here in every single point that you can see are unidentified velocity vectors using the particle tracking velocimetry method, which is also widely used nowadays in hydrometry and also experimental hydrology. Of course, it also has limitations, but what you can see is it's a nice spatial trend, not just a few transects. We can follow the trend, how the river Talveg is speeding up the flows, especially here is the most intensively eroding section. So we can try to match these correlations with the bank erosion trends and the local flow conditions. And of course, if we have bathymetry, if we have these velocity information, then we can derive the cross-section. So in that case, we can provide discharges because we can provide even manually or some AI-assisted way to derive the water level, which is ductile water level. And once we have this bathymetry, we can then provide in every consecutive surveys the appropriate discharge levels. And of course, there will be the question, how accurate is that? In scientific point of view, we tested these and to compare these cross-sections with ADCPs. And what we have found that the deviation ADCP and UV-based water depth is a really nice result, applying several corrections and even the difference in meter per second. And what we also combined the relationship. Of course, it's not perfect, but still we are developing the method and testing it in several conditions. So what we see is it's in an acceptable rate in range. So could be more useful data than the more far gauging station, stage and discharge information. Of course, if you have this in overall, you can combine this with the point cloud generated from the traditional structure for motion. Point cloud, you can see the colorized information on the riverbanks. And in grayscale, you can see the bathymetric point clouds with darker shades, the deeper parts. And as you can see how these point clouds representing the surface flow magnitudes, how they're increasing and how they're highlighting this color on the outer bank and the apex of the riverbank. So we would like to use it for continuous monitoring of the bank erosion processes. If we have a closer look in other river reaches, not just this one, this can, of course, highlight, first of all, the Talveg, as I mentioned, but also if we accept that there's some blank area, we can try to develop a new interpolation method with my colleague, which is under preparation. And also, even it's just a half year difference between investigated river section, what you can see is also, for example, this side, how the bar formation, the point bar formation is taking place, and also how this local scour is developing and intensifying bank erosion. So this can provide really nice high resolution in situ information about morphological changes without the, for example, the multi-beam sonars cannot be applied here. And also here in this setting, what you can also observe is the deepening of this part from a different perspective that I showed before. So these are just a few examples how we would like to implement these into models. Because, for example, the 1D, 2D models are usually missing a lot of detailed information about these small river catchments. So that's why it's also providing nice information. And also how the flow velocities, the flow magnitudes are changing seasonally. For example, in this spring, 2019 shows almost a kind of a nice evenly distributed flow velocities. But for example, in these autumn conditions, that's what I already showed you many times in this lecture, how it intensifies the flow magnitudes. Oh, excuse me. And also, this method relies on control points. So how we would like to scale these images, because these, since the PTV, the particle tracking velocimetry, relies on the thing that we make consecutive images, and then we can quantify the moving objects on the flow. So if we know how much they traveled and we know the time difference, we can estimate the velocity. So we need control points that we survey with GPS. But for example, in floods, this is not applicable. But with the recent advancement with drones, we have RTK drones that they can provide a really accurate direct georeferencing. So this method can be applied in flood conditions. For example, the same area you can see in bankful state, you can see an interesting opposite way of the flow structure when it floods. It's showing an opposite trend, how it slows down within the apex of the river. And we also can use this to track what are the main flow pathways within these, not just the main channel, but also the surrounding point bars in this floodplain. So we believe that these methods can bring a novel understanding of the local processes here. And also, just going to the end of my presentation, not just RGB sensor we apply, because there can be conditions when we cannot track too much things on the surface of the flow. And so we are applying, for example, thermo-infrared cameras, which are in general conditions are not showing too much important things. But for example, if we doing some filtering, we can also estimate flow structure, because the different mixing of the river body or the water body can also show trackable items, and we see if you combine the RGB based and also thermal infrared based estimation of surface flow velocities, this can be also a nice advancement. So also you can read about this in the paper below. And also, why thermal infrared? And there are many conditions when they can also help us to identify procedures that are not visible in RGB. For example, here in the same area, we have a dual sensor in the same time recording RGB and thermal infrared videos. Here we cannot sense anything regarding these vortices. Because this is a remarkable example how the in-train sediment is cooling down and how they creating this local scar and really deep bed erosion here. So these can be also applied if the conditions are proper for this. So this is a set of studies that we apply. Of course, it's a nice teamwork that we usually continue. So we are developing these to continue the time series that we have started to apply all of the models that all of these 3D and 2D flow information that we gathered in the past few years to test it for modeling of this channel morphodynamics. So if you have any questions, feel free to ask, even in the chat and even in discussion now. Thank you very much for the attention.
Hi to everybody. My name is Ioana Perșoiu, and I'm just a second. And I'm from Ștefan cel Mare University, Suceava. I'm a researcher there, and I will switch your attention to larger time scale, late quaternary time scale. So I will talk today about late quaternary fluvial records in the northeast extreme of the Pannonian Basin. Just a second to, okay. For general settings, my study area is located in the Great Hungarian Plain in the northeast part of it, which is the main compartment of the Pannonian Basin, which also is the largest active subsiding intramontane depression in the Alpine Carpathian orogeny, starting with late Miocene and accentuated during Pliocene and Pleistocene. This area registered a compression north to south and east to west, leading to the marginal uplift of the subsidence in the center part here. And during Quaternary, the fluvial systems, mainly of Danube and Tisa, filled the sedimentary basin with 100 meters of materials, mainly sand, silts, and clay, 700 meters here in the center part of the basin, and 100 meters to tens of meters in our study area. So in the evolution of the fluvial drainage of the area, we have two main phases recognized by the former studies. One is concentrated, referred to early Middle Glacial, when this basin was filled with the sediments, and at the surface we see the Danube-Tisa interfluve in this part of the drain of the basin, and Nearsheg alluvial fan in this part of the region, both of them oriented to the main subsidence centers of the area. If we are looking to the last phase of the drainage evolution, we have the last glacial cycle in Vexelian, when occurred large-scale basin scale tectonic resetting, which lead to a dramatic drainage reconfiguration. Here we have three main phases: early Middle Vexelian, when Tisza abandoned the Neersheg alluvial fan and moved to the eastern part of the Great Hungarian Plain along Ermelek Depression, and from there to Mako subsidence area. Then during the Middle Vexelian, around 50,000 years ago, Danube moved 100 kilometers to the west for a north-south position along its former alluvial fan, which is Danube-Tisza interfluve. And the last avulsive moment occurred sometimes between late Pleniglacial, late Glaciation. It was the case of Tisza, which abandoned this eastern part of the Great Hungarian Plain for a western position 80 kilometers to the west. And this last avulsive moment and the impact on the drainage organization is the topic of our study. So once the Tisza abandoned this position, on the eastern ridge of the Great Hungarian Plain started to develop large fluvial fans as the tributaries coming from the Eastern Carpathian and Transylvanian Depression arrived in the area. Here is the Somes. I marked on these maps where is the position of the Somes fluvial fan, the study area of our own study area. So before entering in our main study, I will give you some backgrounds about the known facts about this topic. So it is accepted that the evolution of Tisza occurred 40,000 years ago. Tectonics are the main controls in the development of the large fluvial fans, as I already mentioned. But anyway, studies along middle and lower Tisza show the distinct imprint of climate signals also is visible in river behavior. And the last general information is that meandering seems to be the dominant channel pattern in this area, with temporal coexistence of it with braided patterns, mainly imposed by local conditions. So in these settings, general settings, we have our main research questions will be for Somes fluvial fan will be: what is the time frame for Somes fluvial fan evolution? How do tectonics, climate, and autogenic controls act on fluvial fan formation? And what this insight may say about the evolution of the fluvial fan in the region? What we did in the first phase, we tried to recognize the drainage configuration on the surface. So for this, we mapped all the channel relics, drainage networks, and flood basins, preferentially prior to the extensive hydroengineering interventions from the 19th and 20th centuries. So our basic map, from where we extracted the informations, were the second Austro-Hungarian military survey. But this data, after then, we fitted better with the informations extracted from older and younger cartographic informations. Just to present you very short what we found, based on this surface mapping, we identified 12 channel belts and 4 historical meander belts, which in the end we were able to group them in 5 fluvial lobes. And in terms of general morphometrics of them, based on radii of curvature of meanders and meander wavelength, we can say that the largest meanders were reported in the northern part of the fluvial fan, along the so-named lobe 1 and lobe 2, attesting generalized flow northwest and north-northwest. While in the southern part of the fluvial fan, we inventoried middle-sized meanders of Krasna River, large meanders if we compare with the historical and present day meanders of this river and of Yer, which drain the Yer Valley. And also the third category of meanders are in between the two, associated, the so-named small-scale meanders, associated with secondary flow channels of Somes, and also the historical meanders of Tur, Krasna, and Yer that I already mentioned before. The second part of our investigation was focused on sedimentary and chronological investigations, with the aim to provide a first age control on the active flows along selected channel beds. For this, we took organic and sandy samples, preferably from the upper part of the in-channel sandy units, which test the active flowing along that channel belt, the lower part of the channel infills to have a minimum age of channel abandonment, and the overbank sequences, which definitely attest that channel is not active anymore. Our database contains 21 conventional and IMS radiocarbon ages and 12 OSL ages. So following what we observed in terms of morphometrics of these paleomeanders, we grouped our sedimentary and chronological informations into sections. Here I present you the data as they look like in space and vertical relationships in the northern half of Somes fluvial fan, where we grouped our investigations for lobe 2 and lobe 1. The main information that I want to extract from this graph for this presentation is that the maximum ages were recorded in lobe 1, around 50,000 years, but this is an age that is overestimated due to partial bleaching. So we keep it in mind, but we don't consider it at our interpretation. And the next two oldest ages are in the lobe 2, 30 and 28,000 years. So the second observation is that time range of the samples in the lobe 2 cover an interval of 30 to 7,000 years, attesting that Somes flowed in the north-northwest direction along lobe 2 during late Glacial and early Holocene. Here are some examples how the field looked like. In this picture, we have the example of the braided channel in along lobe 1. And here in lobe 2, the large meanders that were dated to 10,000 years old. The second group of sedimentary and chronological investigations are grouped for the southern part of the study area. So lobe 4 and lobe 3. Lobe 3 is reflect the activity of Krasna in the area. And for it, we obtained ages between 13 and 3,000 years, which attest the flowing of Krasna to northwest, starting with late glacial. While for the lobe 4, which is of present-day Somes and its associated channel belts, the ages between 5,400 years attest its presence starting with Middle Holocene. And also some examples along the present-day rivers of banks of the Somes and paleochannels investigated in along lobe 4. Then, with all this data, we started. We go now to the next level to try to give some answers to our research questions. So, in terms of what is the time frame for the Somes fluvial fan to evolve, we return to our first image on where this fluvial fan is located, and we grouped all the informations on this generalized map. So the idea is that the oldest oldest fluvial remains are recorded in lobe 1. These are only relics because they are most of them buried below the youngest materials of lobe 2, 4, and 5. Then the following in age is lobe 2, which attests the northwest direction of the Somesh. Northwest direction of the Somesh. It was constrained between, it was active between 30,000 years and 5,000 years. Then is in age, the next in age is lobe 3 of Krasna, and Krasna moved from Yer Valley to northwest, sometimes between between 60 and 40,000 years ago. And the last fluvial lobe is of Somesh, when the Somesh abandoned its lobe 2 direction for its north-northwest direction for a northwest direction 5,000 years ago. So the next question is, how do tectonics act on fluvial fan evolution? Just a general information where what is the tectonic background of our study area. It is located at the intersection between the two main fault systems in the Great Hungarian Plain, the Mid-Hungarian Fault Plain and the Transcarpathian Fault Plain. Here we have a more detailed picture. What I just want, I will not go in detail with this, but only I will highlight that in the area we have many local scale horst and graben structures which move separately and in a generalized subsidence setting. In between the two main fault systems, we have a local graben system named Satu Mare graben system. So actually we have 3 compartments with different behaviors of the Middle Hungarian fault line, Satu Mare graben system and Transcarpathian fault line. So what can we say when we compare this internal, so this detailed tectonic informations with our reconstruction of lobe formations, lobe generations? So we can start our history of tectonic influence with the moment when Paleotissa flowed along the Ermelek depression at the eastern part of the study area. This was in early Middle Vasilian. We don't have an age control for this phase. Then the next phase, the subsidence along the Transcarpathian fault line, along the main fault in the area, Halmeu fault, started to increase. And this forced the Tisa to abandon its eastern position for a northwest position. At that time, and this moment occurred before 30,000 years ago, and the relics in the area are recorded in lobe 1.
Anna,
in the meantime,
excuse me, 2 minutes left. 2 minutes left.
Krasna continued to flow along Ermelek depression, and then I will just move quickly how the river continued to the Somesh continued to flow to the north-northwest, and then everything moved to the Somesh graben system, and the last phase is when Somesh also moved to the northwest. Then the third information is related how the climate and paleoenvironmental conditions influenced the channel pattern evolution. I will go very quickly through this. The main information that we collected, both about the paleoenvironmental background and the fluvial activity in the area, sustained that meandering remained the main pattern during the Middle Glacial and Holocene. if we want to place this picture in a broader context, we can see that this behavior is restricted to the subsidence area of the Great Hungarian Plain, because in the upstream and farther to the west, the braided pattern with coarse materials are the dominant fluvial typology for the most part of the middle planiglacial, middle and late planiglacial. This is an example of how the materials looks like, the braided patterns. The middle late planiglacial are present in the Transylvanian Depression in the upper part of the drainage basin. And this discussion and these informations leads to the proposal that an additional explanation for the dominance of meandering in the Great Hungarian Plain could be related to the limited sediment connectivity along these drainage basins. So to conclude, in case of Somes fluvial fan building via base level changes linked to differential local tectonic block movements and climate and autogenic factors acting at millennial and centennial scale times modify style and patterns of individual fan lobes and at the regional scale implication, the large fluvial fans along the eastern edge of the Great Hungarian Plain started to form more than 30,000 years ago, supporting an earlier moment of distribution to the west, while meandering and are the dominant late planiglacial Holocene channel patterns. Indeed, they're as reported elsewhere in the area. And we ask if the drainage basin control could be also a good explanation for this. Thank you for your attention and sorry for this long talk.
Thank you very much.
I'm Akhtar Zeb Khan, basically from Pakistan, and I'm a doctoral student at the Svalbard Academy of Sciences. My presentation is entitled as Geomorphic Recovery of the Bela River after River Training. As it is clear from the title of my presentation that it is basically composed of two major components. The first one is the geomorphic recovery and the second one is river training. In an era of river repair, when we are talking about the geomorphic recovery, it is being the central part of the river management practices. But until the early of 21st century, there were no any coherent structural framework to forecast the river recovery potential. At that time, the river recovery were really slow, and the debates continue for a very long time that what actually a river recovery means to be. So according to Freris 2015 and Rinaldi 2013, geomorphic recovery is basically the assessment to compare the disturbed reaches with reference conditional reaches for a particular river type and to interpret the driver of changes. It means it is a natural process that reflects the self-healing capacity of a river, or is the multiple evolutionary time slices representing different stages of geomorphic adjustment. And what actually a river training is, it is an engineering component that is usually used for the structure measure which are taken to improve the river and its bank for the safe mitigation of flash flood or in general flood control measures. This is actually the river evolution and recovery diagram. I have copied it from the approaches of Freris and Braley 2016. This diagram is basically categorized into 5 major components. The first one is the intact condition of a river, where the reach is at the intact condition at the top of the degradation pathway. As such, no any type of modification or alteration has been evident from this from the part first, as it is located at the original condition. But on the second one, I mean the progressive adjustment, the reach start deteriorating from the original condition to the degradation on the degradation pathway. It means some of its component has been lost, and but still it is operating in the same condition, mean it is the same the body of the same river type. Here some of the and the third one, some of the restoration measure have been taken, and the river is going to be the reach is going to be restored to its original condition. And a minimum intervention is required to bring it back to its original condition. And the fourth one, the reach is the poor condition, mean it is far away from their original position and on the degradation pathway. And some of its component can be restored, but it is almost impossible to recover it to its original condition. And in the fifth one, where it crosses the threshold and it is at the lowest position of the degradation pathway, mean now it is operating as isolated body or as isolated channels. This figure has been, aerial images has been copied from the approaches of Kedoa 2013. It is from this images, it is clear that how the river morphology has been evolved with the passage or changes with the passage of time. This is started from 1949 till 2009. And it is quite clear from these images that how the river morphology has been changed with the passage of time. And the second one image is clearly described that how the negative impact of the river training on the river morphology. This image has been taken from in 2015 and the other one is 2018, and you can compare both of them. That how the river impact, river training impact the natural diversity of a river. This is actually my study area, the Bela River, which is located in the northern portion of Slovakia, originating from the two main tributaries, namely Taichi Potok and Koprovskaya Potok. It is a 23 kilometer, almost 23 kilometer long river. It is the main right and main tributary of the Wah River and draining the Lipto Basin in the northeast and southwest direction. But the main question arises here that why Bela River is so much important to have 4-year detailed investigation. It is because of its geomorphological and ecological importance, being the unique and high energy multi-thread river system belonging to the protected area of Natura 2000. And the third one is because of its ongoing geomorphological process and their adaptation after Incentio River training in 2018. My research aim is basically divided into two major components. The first one is the main component, which include to identify the natural geomorphic recovery phases of the braided plain area after river training, which is happened in 2018. And the second one is to understand the geomorphic adjustment in channel landform to continuous erosion and deposition by natural mean. The second aim of my research is categorized into four major steps. The first one is to assess the hydromorphological lateral connectivity between the braided plain and floodplain area. The second one is to the detection of vegetation dynamics. The third one is the development of the process-oriented model for the river recovery potential. And the final one is the recommendation for future river management regarding the study river environmental status. These are my objectives, which we have to cover in our research. They are also categorized into 5 major components. The first one is climate change impact on the river morphology based on the sediment transport, their depositional rate, and their mutual interaction. The second one is the vegetation dynamics in the context of flood events with low or high recurrence interval. The third one is remote sensing and GIS-based modeling approach for the river system geomorphic recovery and evaluation. The third one is the creation of geodatabase by innovative geoinformatics method. And the final one is the society involvement, their perception and sustainable management strategies after the previous inappropriate management intervention. These are basically the methodological and conceptual framework of my study area, which is basically categorized into 3 major components. The first one is the theoretical approach or the literature, which is further categorized into 5 major groups. The first one is what is mean by a recovery concept, that how a river will recover itself with the passage of time. The second one is a biogeomorphological concept, that how riparian community or the bio community interfere or have a place point on on the river recovery. The third one is a natural based solution concept, that how the river will be recovered with by a natural mean. The fourth one is the passive restoration, and the final one is the basically the policy environment or the implementation of the policy, European policies. The second one is the field investigation. And field investigation, we have to measure all of these components. Suppose river reaches, we have to monitor, compare the reach, evaluation of the reaches, and then a river training impact, that how the river reaches has been impacted with the passage of time by the river training. The second one is, I'm sorry. The second one is the cross-section measurements. We will have to make a certain type of cross-sections by different means, sediment processes, that how the sediment have been processed in our catchment area. It may be erosion, transport, deposition on the basis of their texture, composition. All of these will lie in this category. Then vegetation dynamics, and finally discharge condition, flood and drought condition. These are the remote sensing data which we will collect in our research by means of aerial photos, LiDAR data, unmanned aerial vehicle images, and digital elevation model. And by interpreting all of these measures, it will lead us to the modeling approach. This is basically the conceptual modeling approach. We are here. We have started at the beginning of November or at the end of October. So this is just a conceptual modeling approach. It may be modified with the passage of time, because we are at our literature review page now. Basically, it is categorized into two major components. The first one is geomorphic trajectories prediction, and the second one is sediment transport and surface water flow simulation. Geomorphic trajectories are basically divided into two major components, will be composed, categorized into two major components. The first one is a morphological quality index. Morphological quality index is basically the physical, to deal with the physical habitat of the river or the catchment or the watershed, where we have to categorize the fluvial system and on the basis of their elevation, slope, on the basis of their sediment transport, their discharge, and many other characteristics. Then we will compare this categorization with the past morphological environment, that how the river and these categories perform in the previous environment, and then we will evaluate the current status of the river. And when we evaluate the current status, then we will determine some recovery potential, that how the river recovery potential will be in future. And then we will target it some condition, that suppose this condition will happen with this result. And the sediment transport, this can also be modified with the passage of time, because I have mentioned Hay-Cross model, but it is possible that we use a Cassier model, means cellular automation and elevation, slope, and river model for my research. But in both of these models, there are almost the same parameter utilized. So we will have, first of all, we are working on hydrological modeling, mean HMS. And then we will utilize hydrological modeling by means of Hay-Cross or maybe Cassier model. And then it will give us the flood visualization and mapping. And for 1D and 2D, it will give us the validation of our results. These are the references. Basically, I have studies and my research till now. These are the framework of my research, that it will take this time, from this time to this time, we will use this methodology, or literature review, data collection, and data analysis write-up, and my final thesis write-up. I hope it works. And thank you so much. If you have any question, I'm sorry, we are here from the, we have just started at the beginning of November, so we don't have any, results for our thesis or something like that, but we are working on it. I hope maybe in the next session we will give you some results.
So, ladies and gentlemen, I hope you see my screen. And let me take you to the more tectonically peaceful area of Bohemian Massif, more to the west, because there was no presentation about Czech Republic during this seminar. So this presentation is only part of my defended thesis, which dealt with evolution of valley in Poland, in southern Poland. It was the river of Biała Landecka, and it was quite a challenge because I need to find out how to get information, how the drainage network was developed since, let's say, Miocene to today. So I started to convert from geomorphology to structure geology, because this was the only way how to do that. And this presentation is only part of it. So I will present you something about stress field changes since late Miocene, when this drainage network was, let's say, started to develop. So what was the aim of this research? All of us are geomorphologists, and the main role in landscape evolution play undoubtedly the tectonic activity of faults, and the faults are somehow behavior, and this is all driven by stress field parameters and stress field acting. Let's say mountain evolution is driven by paleo stress field evolution and acting, and also nowadays present-day stress field still acting and causing us present-day earthquakes and so on. But we have a little problem with it, which is now you can see how the stress field influence the fault behaves, and how the mountains or landscape is evolving in different tectonic regimes. But we have the problem because from the past we don't have enough information about the stress fields, and it is quite a challenge. We know very well, not very well, but somehow we know how the stress field is behaved today. We can see, for example, the amazing world stress field map, which includes several measurements of stress field around the world. But as you can see, in our region of Bohemian Massif and also in Ukraine and so on, we don't have enough information about how the stress field is behaving now. What about in the past? We have only several information from the past. So that was the aim why I started to deal with the past and also the present day stress fields. So the methods are two main, and then these two methods were applied to how the landscape was evolved. So the first method I used was the determination of paleo stress field parameters based on the stria on silicon sites in dated volcanic rocks. The advantage of dated volcanic rocks is that if you have some stria in these rocks, you very well know that this needs to happen after the volcanic rocks volcano rock start to exist. So all silicon sites, all strias in silicon sites are younger than the volcanic rock. And there are several methods how to date very precisely the volcanic rocks. The second method I used was the studying of present-day stress, studying the micro displacements registered by deltometers. I will show you how it looks like later. So my study area was on the border from Czech Republic to Poland, in the northeast part of Czech Republic, in the Sudetic Mountains. I studied one tertiary volcano, and the deltometers were placed in the gallery, the small gallery, which is right next to the volcano, let's say half a kilometer from this place. So the first method dealt with the study of stria in volcanic rocks. Here you can see how the strias in volcanic rocks looks like. There are several generations, and we measure the orientation of the silicon site or for the fault plane, and then the orientation and dip of the stria. Here you can see that we had several types of stria, rough ones, the fine ones. We took some samples of it and try what we can to do with it. But mainly we collect the data for data sets for the orientation and the dip of these strias. Then we did the well-known paleostress analysis, which is quite complicated. So first of all, you need to collect the data, and then separate these measured data to homogeneous data sets. It was used two softwares. One was developed in our department in 2014. It's called ROC 2014, and the other one is well known from Allmendinger Foltkin. Then these softwares can give you the parameters of stress fields and somehow more or less automatically separate the data sets to the homogeneous one. So you have the subset of stria which were created by one stress field, and then the second with other stress field. We also verified these data by using the slip tendency. So if you have some plane or silicon size which is badly oriented to the stress field, it can't move. And if it is in this subset and calculated in this subset, you need to put it out from this subset, because it is not possible to move with this silicon site in this stress field. And also the last thing was to compare the founded stress fields with the known one or with the sedimentary records from other authors in this area, and compare it whether it is possible or it is not possible to have it. So here you can see in the lower part the situation of the one little volcano in Lutynia in Poland. It's near Late Zdrój, the most famous spa in Poland, and there were also 3 lava flows from this volcano, which were opened by mines. So you can measure it in mines. These rocks. Here is how it is look like, and we found and these lava flows are dated. So you can see that here are 3 very precise very precise data. So we found there 6 different paleostress phases, and we know that they must be in this order. So it starts with paleostress phase A, which is at the end of Miocene and start of Pliocene, and then continue with some it was compressional one, so there we expected that the mountains were rising, and then switched suddenly to the transtension or extension regime. And then once more we found the compressional one, which is not known yet from other works, which was at the end of tertiary, and then the two extensional regimes, which were somewhere since 3.83 million years to today, because we don't know, there was no other volcanic rock dated where we found it. The second method we use to record the present day stress is based on this device, which was developed in 70s in our institute. It is able to measure quite precise displacement in 3D. So if you place this device to the gallery, here is some example from this gallery. There are observed 3 faults. You can see it nicely on the pictures. You stick 2 iron tubes to the blocks, one on one side of the fault and second on the second side of the block, and then place this device, which has 2 pairs of glasses, one in horizontal plane and second in vertical plane, and there are 2 pairs of glasses. In each is the spiral, and if you move the spiral against the second glass, you get the moire effect fringes, and then you can recalculate it to the displacement in vertical and in horizontal plane. So these devices are quite common now. Here you can see where everywhere are placed these devices. We now have semi-automatic and automatic reading of this and calculating of this devices. So now we are moving to the up-to-date monitoring of faults in Europe, but not only in Europe. And here is the results from this gallery. So you can see there are 3 devices. Here is the displacement, because I told that this device can measure quite very precise. It is like the 100th of millimeters per 1 fringe on the moire effect. So you can monitor very precisely what's happening in 3D on the faults. And if you give it together, you can find that there were several episodes when it was moving, and then you can notice that there were some period when it was more active movement and then less active movement, and the movements were more or less simultaneously on all 3 devices, which is fine. So it was defined, let's say, 40 individual time events, displacement events in this gallery, and calculate the stress which caused these movements. And here is the result. So we found 5 tectonic phases. 2 are quite similar, these 2 and these 2. So there are, let's say, phases, tectonic phases different, which are switching through the time. So you can also, based on these known of the parameters of the stress calculated from this, you can calculate also the planes which are very well oriented and can move in this stress field. They are in this last column. And if you compare this was from the first method, and this was from the second method. It is the nowadays stress. This is the old stress fields since late Miocene, and compare the orientation of these well-oriented planes with high tendency to move in this stress field with existing and known faults in the area.
Excuse me, 2 minutes left.
Yeah, okay, I will finish in short. You can get the segments of faults which can move in which could move in this stress field. So here you can see, for example, in the first one, it is the Miocene one, end of Miocene one, that there were several segments which can move in this stress field and how can move. We also don't know the depth of these faults, so it is also interesting, the important part of parameter, but these they are quite old faults, and they are more or less subvertical, all of them, majority of them, so we can model it for the vertical ones. So, and you can also do some reconstruction, how how the landscape will behave in these stress fields, and then you can compare it with other known, for example, stratigraphic things, and you can say that these stress fields were acting the main role in evolution of Sudetic mountains, not only in Bohemian Massif, but I think in the Central Europe mainly. So there were several events when the mountains were rising. It was during the compression, the blue one, and then when it was relaxing, and just let's say the other erosion and other phenomena were destroying these mountains, and then once more rise the mountains in compressional regime. So thank you for attention.